Now we're going to talk about a subject very dear to my hardware hacking heart, apparently microcontroller programming Zen, or advanced microcontroller programming for those of us who love AVR chips. And with us is Vincent. At the end, we'll have about 10 minutes for questions. So you should either come find me or go to the mic near the AV guy. And Vincent, if you could please repeat the question, then
sure.
The camera will pick it up. Thanks a lot. And will everyone please give him an excellent welcome.
All right, thanks. My name is Manuel Ovesen, and I've been building software for microcontrollers for a few years now, and started doing it like pretty intensively for the last year. I held a talk last year at the Congress about devices and building MIDI controllers, doing music with them, and I've basically spent the whole year programming firmwares for not exactly this CPU, but this kind of CPUs. So I wanted to ask who is doing microcontroller programming here? That's pretty nice. Who has been using the AVR microcontroller? All right. And who has been using C++ on the AVR? Okay. Yeah, basically, I call this talk hardcore microcontroller programming. I think in the description of the talk, of the first description, because my goal was to show like a lot of incredibly complicated hardware details and programming details that I discovered during this whole year. I basically revised the setup a bit, that I'm going to be like more general, not go into too much detail, because basically the whole framework is open source, and you can find all the information on our website at ruinvesen.com. You can find me on Twitter as well. If you have questions, you can send me an email later on. So what I've been building in this company, I started about 1.5 years ago, is MIDI controllers that look like this. And the concept behind those controllers is that basically the whole hardware and software is open source, and you can program your own patches. And it wasn't this way at first, but for the Congress last year, I prepared some workshop environment about programming, started using code sketches like on the Arduino for this device, and this is basically where the whole framework I'm going to talk about stems from. So basically this device is connected to a synthesizer or to multiple synthesizers using MIDI ports on the other side, and you can use the knobs and buttons to trigger effects or do some crazy stuff. The device inside, the CPU inside this one is a NetMega 64 microcontroller, so it's basically an 8-bit microcontroller with 4 kilobytes of RAM and 64 kilobytes of flash. I added some additional RAM because 4 kilobytes really is too limited. And basically built what I call the MIDI-Duino framework, which is this huge framework used to control the whole GUI thing, so that basically you can build pages like Windows. You have directly an event system for the whole GUI, like if you press a button, you'll receive an event. There's some MIDI parsers, there's some code to interface with specific synthesizers, all kind of stuff. So it's basically 30,000 lines of C++ now. Some parts are in assembler, some parts are in C. But basically it's become this huge object-oriented framework. And you can all find it on GitHub. I think I have the URL on the last slide. So if you want to check it out and use it. And what I'm going to talk about basically is when I started to build this whole thing, I started like using the techniques I knew from traditional software development, agile programming, which is kind of this buzzword, which means that code has to be flexible and the way you interact with it is flexible as well. And it's not a view that is very common in the embedded industry, because you basically build this one firmware and flash it into the device, and it's never going to change anyway. So you don't have code as flexible as on a normal device. And then you have these huge restrictions that you have like just a few kilobytes of RAM, which make it much more complicated in a way to do refactoring, to do unit testing, for example. But I started to think like if you're clever, if you build some scripts, if you just like bring over this mindset to embedded, you're gonna find some pretty nice stuff. So basically, this first part of the talk is going to be about agile techniques applied to embedded programming. The second part is going to be about using C++ in an embedded framework, what kind of things do work on an AVR, which don't work, what you have to be careful about. And the third part is going to be about optimization, which is a huge task, actually. It's basically part of everything you do on embedded programming is optimizing code size, optimizing speed. And then I'm going to go into a bit more technical details about timing, latency, and real-time requirements, which are especially interesting when you're building musical instruments. And the final part is going to be about debugging techniques, like what kind of stuff do you use when you debug that kind of environment. The whole idea behind the microcontroller is I started using CNC as well, so this kind of all goes together, is rapid prototyping of devices and of firmwares. So you have this MIDI controller and you want to try out a few ideas, and if you start to use like all kind of development techniques for it, you're just going to spend like 2 days building make files, building like harnesses and stuff like this, and that was basically too long for me. So last year I built this, I used the Arduino editor, replaced the whole libraries, the whole code for it to work with my device. Now I can just like write a few lines, say if you press this button it's going to send a note, if you press this one it's going to reverse the sequence, for example, and then just try out pretty quickly the whole way to approach this. I can use that for GUIs, but for devices as well, like having scripts that take an eagle file, just like build a device, build a whole casing as well. You just like have to put it on the mill and it's going to generate the device. So actually I'm saying like things in a sentence, and it's a huge amount of work behind it, which you can check out from the Git repository. For example, this whole software that generates the CNC files is like a few thousand lines long, and it's very interesting, but I'm just going to skip the whole hairy detail thing. I think you all know the Arduino platform. I kind of use the same idea that you just have like this one connection to the PC, which in my case is MIDI or MIDI USB. And you use that as a bootloader, but also to interact with the device. So you plug in the MIDI controller over MIDI, and the bootloader actually understands MIDI, so I don't have to replug cables every time trying out something, and just have this whole kind of test setup. And then don't need a program, I don't need anything, I just have this normal environment. And it's actually, that made the biggest difference, I think, in the whole way I approach this development, is that you can, if you want to upload a test suite, for example, you just have to press one button and it checks the test suite, sends the results over MIDI. I have a profiler that works over MIDI, so it sends me like profile information while it's running, and I can interpret it at the other side. Some pretty interesting software we have as well is a patch manager, which is kind of an app store where users can click different firmwares for the device and just like press upload, and they have like this description of the firmware. I can actually show that, which looks like this. So you have basically this software. You can click on the different firmwares, you can read the documentation for it, and then just press upload. It's going to show the MIDI ports, and you can upload the new firmware. So all kind of ideas that stem from this sketching Arduino platform idea. I didn't actually use any kind of Arduino code or Arduino stuff in there. Another very important part of the whole agile development is using source control, which funnily is not that common in embedded development either. Like you have the few projects I worked on, you had like all these test 1, test 2, test 3 directories for the source code, but it's actually pretty crucial if you want to have good firmware support. So I basically check in the whole source code for a special revision of the firmware I ship to customers, and then I can go back and have exactly the kind of same setup, have the same RAM problems, for example. And one pretty important point of the whole thing is to check in the toolchain as well. Like when the toolchain changes, you're going to have different assembler code, and due to the restricted resources, you're going to have a lot of problems if, for example, a multiplication takes one cycle more in this one case than in the other case. With Git, which I discovered this year, it's pretty easy to do branching, merging. If you try out a new feature, do your refactoring in a branch, and then take it back to the main branch or not, depending on the case. Yeah, basically every kind of change you do, just do it in a branch and then merge it later on. It's very easy to bug fix and refactor stuff, especially stuff you ship to customers, or like a special version you ship to a special customer, which turns out to have a problem, and it turns out that maybe the compiler is broken, for example, and I can still trace that back 3 years later because I have the whole tool chain, the whole build environment included in source control. What's pretty interesting as well is when I upload firmwares into this patch manager, I have a script that's going to tag it, and then I can just say, yeah, did you download it from the patch manager on this day, which is the ID, and go back and kind of check bugs out. I'm going to go into this into more detail in the whole debugging part of the talk. And another agile technique I use is unit testing, which is actually kind of complicated to implement on the hardware device because test suite are normally a whole big amount of code because you have like all these test cases. So it doesn't fit on the device usually, or you can fit like 50 tests on it, and then you have to reflash it and then execute another 50 tests. So what I did is build mock objects for basically every kind of hardware feature there is on the device using C++, which I'm going to go in later on. So I have like a virtual MIDI interface, I have a virtual encoder, I have a virtual timer, and I can basically execute most of the unit tests on the host itself, so it runs in a few seconds, and I can see when I'm doing refactoring that maybe the latency of the MIDI protocol parser is not going to be good enough, for example. That's really, really useful for refactoring, like when you start to have this big framework, you spend most of your time just slightly redesigning APIs, for example, or replacing an object by another, and it's actually pretty crucial to execute it. One thing I'm working on is using a simulator to basically execute the whole test suite and like log different stuff inside the simulator, so it runs in a few seconds, and I still have the hardware approach, the real one. And the last part of this whole agile stuff was basically project automation. Like I have this big code base, and I'm at the moment the only person working on it. And every time I do a change, I basically have to update 20 different firmwares and tag it and update the documentation. So it's actually pretty cool to use an automated system like BuildBot. With every time I do a code, it's going to regenerate all the firmwares, regenerate all the documentation, run the unit tests, and basically update the patch manager as well. A pretty cool thing is using this information as well to plot different parameters of the firmware, like the code size over time, so I can see which revision just added a few kilobytes at this part, or which revision just destroyed the latency, for example. Because I can plot all these kind of hardware-specific information and store it as well. So that was basically a short overview of the whole agile stuff, and you can check out the scripts in the GitHub as well. And if you have any questions, you can ask me later on. So I'm going to go over to the C++ part. Who thinks that C++ on an 8-bit microcontroller is like a heresy? That's a view you find pretty often. It's one I had as well because I come from assembler programming and C programming. And I was like, oh, C++, it's just going to be awfully bloated. And actually, it is. It's like C++ is kind of this monstrous language. It has like 10 different sub-languages. You have like a normal C part. You can write C in C++. Then you have like this object orientation part. You have templates, and then you have like exception and a whole kind of exception mechanism. Then you have STL and like memory allocators and operator overloading. So it's basically like this big octopus with like different kind of languages waving around. And if you try to use them all, like there's a few books like Modern C++ Design. It just makes my head explode when I go to the second chapter. Can we turn the lights down, or is that on purpose? Anyway, it's like this multi-paradigm language. But what I learned to love about C++, like coming from Lisp as well, was like what is this object orientation where you have to use virtual if you want to overload a method. It actually makes sense if you look at it from a pretty hardware-near point of view, because you can basically control exactly which byte of the memory is going to be used by what, and how function calling is going to work, what the overhead that's implied is. And it actually makes kind of a lot of sense. And if you're pretty careful and the compiler is good as well, you can basically produce code that's pretty much what you would have written in assembly. That's what I built this ring buffer with a template to generate like ring buffers of different sizes and of different memory types. And basically, you're pretty careful when designing ring buffers to have like a size that's a multiple of that's a power of 2 to be able to do like modular arithmetic to do masking for the modular arithmetic. And when I first built this template in C++, this ring buffer with a template in C++ and looked at the code, and it was actually better than what I had written in assembler, I was like, this is perfect. I just need to write one line for a new ring buffer with a different size, and it's pretty much exactly what I wanted. So I settle on a subset of C++ where I basically don't use any kind of dynamic allocation, like there's no new, I just do it with static initialization, which has its own kind of problem. I'm going to come back to that. I do use multiple inheritance because that's pretty useful when you build a GUI framework, and using callbacks, you can just like inherit from this callback class and are able to pass it around with static type checking. I use method overloading pretty much as well, because you have like pages or encoders that are going to be included in containers, and then it makes sense to have like virtual method. And in this case, like when you use a virtual method, it's going to add a function pointer table to your class, and it's going to add a separate lookup before you do a function call, a method call. And in those kind of cases in C++, in C, you would have used a function table, so you would have done exactly the same, basically. And what I use pretty often as well is templates for data structures. I don't use templates for any kind of weird compile time pointer voodoo or stuff like that, but that may be something I have to look into. Templates are still like a bit of black magic for me. But the biggest advantage of the whole thing is basically object orientation. You can encapsulate functionality behind objects. So for example, the whole hardware elements of your microcontroller, the serial UART, for example, or the LCD connection or the SD card, that they are all wrapped in objects. I basically just need to instantiate a specific, I just need to subclass it to adapt it to a specific device. For example, if I have 2 serial UARTs in C, I will always have to kind of build a specific structure, and then it's just all easier to do with objects, basically. And you can, like, for example, the whole USB stack I built for the USB versions of my devices, have 3 different versions of it. One that runs on Mac OS X, one that runs with a separate USB controller, and one that runs with an NatMa USB controller. And except for a few lines of code for sending the actual USB messages, the whole functionality behind it is the same. I can just like subclass it and instantiate it. The big advantage as well is that those mock objects I use on the host to like hide hardware features behind something. And I don't know if you've used C, you basically know the fdef hell. When you start to support different versions of your device, you basically clutter in your whole code with ifdefs and ifs, and to like enable different parts. That's stuff you can do pretty easily by just subclassing and adding the stuff you want, or using multiple inheritance to have different features. What's pretty useful as well is it's just more readable to use object-oriented data structures. Like just a single linked list is just going to be add and remove. And in C, you will have all these kind of weird underscore kind of functions and passing the pointers all the time. So it's basically the huge advantage, and it just enables you to write code much faster, even on the embedded device. I mean, you can still use assembly if you want to, but you can integrate into C++ as well. Which brings me, like, the bad thing about C++ is it's pretty bloated, especially with G++, which is a good compiler, but it just has a few things that don't work out very well. And that's going to be the next part of my talk, which is code optimization. There's 2 kinds of optimizations. Basically, you can optimize the speed, so that the device is not very fast. It has like 16 megahertz and has 8 bits, so it's not very blazingly fast. What I found out is basically speed is not, most of the time, it's not really an issue. It's an issue when you're doing your latency and timing critical parts of your code, but basically the rest is, you're not doing much, you're not doing crazy math functions on it. What's an issue though is if you use 8-bit, 16-bit or 32-bit types for integers, for example. If you use 16-bit, the code is going to be 5 times as long and 5 times as slow. And if you do 32-bit, it's going to be like 12 times as slow, because just like splits it all on 8-bit operations. So that's something you have to take care of if you have a counter, for example. Just knowing that if you have a 32-bit counter and compare it, you're just going to have a much slower and bigger code. So you can use floats as well. I wouldn't advise to do that, because it's... but well, what you can do is basically to see where all the speed issues come from is to use a profiler. So it's actually pretty easy to build a profiler on the atmel. What you do is you just look on the stack frame with a pointer, look where the calling address is from, and send it over to the host at a regular interval. And you can just basically interpret it on the host with some, I think it's called add2line, which takes an address and gives you the code line in the source code, and then you do some kind of plotting of that with a Perl script. So it's actually pretty easy to build. It's like 20 lines of code. It sends it over the MIDI platform. It has a bit of a performance impact, but it's actually pretty cool to see how much time is spent in the big run loop. Or if you see that like 80% of the time is spent in the UART code, you know, okay, maybe I should revise how my UART works. And the whole code for the profile, it's basically pretty portable, and you can look it up in the Git as well. But the biggest issue in the whole embedded programming is basically code size. I have 64 kilobytes of code size, and the newest firmwares are like 60 kilobyte big. One major reason for that is C++, actually. It does a lot of pointer arithmetic because the whole class information is stored in the structure, so it's always looking up the pointer to the class and then doing some indirect addressing to get the member variables. When you call virtual pointers, you have the same kind of double lookup that happens, and that adds a lot of pointer arithmetic. And GCC is not very clever using the extended registers of the AVR. So basically, most of the time, it just like reloads stuff from the frame pointer. Does some 16-bit addition and subtraction and multiplication, and it just like bloats your code a lot. That's, I think, because most of the optimization for GCC are not aware that you're running on an 8-bit CPU, so it may be that there's some kind of stuff happening there. So basically, you have to be pretty careful when you use arrays of objects, for example, to organize the accesses so that it doesn't do a big bloat. Using intermediary pointers works pretty well, for example. Another big issue is when you use templates, you have a lot of code duplication taking place that the linker doesn't recognize. For example, if you have a ring buffer of a pointer to an 8-bit value and a ring buffer with a pointer to a 16-bit value, is actually exactly the same assembler code, but just generates it twice and links it twice into it. So you have to be careful when you use templates and data structures and lots of different specialized data structure. Is just going to be duplicating stuff all over. And a big gripe I have with G++ is that it just doesn't optimize my static constructors. Like, I'm not using any dynamic memory allocation, and it just generates a new constructor for every object I instantiate and just links it in with static values that just copied into memory, and that's it. So I think on my new firmwares, it's like 60 kilobytes of code, and then about 40 kilobytes of that are just static constructors. So it's pretty horrible. A big hope I have is that LLVM is going to be working on the 8-bit CPU pretty quickly on the AVR. There's support going on, so if you want to contribute. And it basically shrinks the whole code at link time and just rips out all the whole constrictor stuff. And my first tests were like 60 kilobyte with GCC and 12 kilobytes with LLVM. In the article and the proceedings, I have a whole part about compiler flags optimization. That's the easiest way to get some bytes out of it, but it's a bit try and error. What's very important to actually do some kind of sensible optimization is look at the output of the compiler. Like, the compiler does a lot of stuff wrong sometimes, and you need to be able to read the assembly. Not maybe write the assembly, but being able to see how it resolves member lookups, for example. You can plot sizes with a lot of the toolchain utilities, which I talk about in the article as well. And what you need to do as well is maybe to understand how C++ works when it's compiled is just build a lot of dummy programs and look at the assembly output and then try some stuff to see how the assembly output changes and see basically how G++ interacts with it. And it changes with every GCC release as well, so you need to do it over and over. And actually, this knowledge of being able to read assembler programs, maybe write some of them, it turns out to be really useful later on when you're debugging stuff. I'm going to talk a bit about refactoring for code size. A few of the tricks is basically avoid big switch statements. That's like the worst thing ever. And if you have a big switch statement, just use a function pointer lookup table, for example, with different states. What's very useful as well is when you have big parsers, which I have, for example, for synthesizer dumps, like the settings dump. I have these huge parsers. It's much easier to build stream parsers that just take one token at a time because you avoid having the need for a big buffer of a few kilobytes in RAM, so you can just basically parse the stream as it comes in. That's a huge space saver as well. What I mentioned already is reorganizing array loops. If you have like indirect addressing taking place, just using temporary pointers to tell the compiler, no, I need this value, just please store it in the register, instead of computing it all over. And a lot of those tricks are available in a book that's freely available online called Small Memory Software, which has a lot of patterns about how to shrink specific cases, how to design your software for a small memory, both code memory and data memory. So that was the part basically about optimizations. There's a lot of details involved. And I mean, if you want the smallest code size, maybe the best idea is just like to use the next bigger processor if you can handle it price-wise. I don't think there's not much need for completely writing an assembly anymore. A few people still flame me on mailing lists for that. So that was the part on optimization. Are you following from the technical kind of stuff, or am I too quick? Because this is going to be quite technical as well, which is timing and latency. And I'm building these MIDI controllers, which doesn't sound like a big issue at first, but it's actually one of the hardest real-time requirements I had. Like, for example, if you want to trigger a bass drum that's supposed to be sounding at exactly the same time as another bass drum, like basically every microsecond is going to make a difference in the sound that comes out because the sound can phase. So even like small shifts, you hear them pretty well. It's not like they're big. They're bad on a timing point of view, but the ear is so precise that you can actually hear stuff phasing and hear stuff that's out of sync pretty easily. So it's actually turned out to be a pretty big issue, is the whole real-time part of music that you need to have low latency when I press a button and a sound is triggered, for example. The second biggest issue, which happens a lot in music, like especially with MIDI and synthesizers, is that you synchronize multiple devices together so they run in the same sync, and then you start to have problems keeping up with the counter, so you're always at the same bar. Like you couldn't be in sync, but then just out of phase. That can happen pretty quickly if you're not careful. And the biggest issue is actually synchronizing. So one of the possibilities is just to take incoming clock messages, which are like a metronome running pretty quickly, giving me the sync, and just react on every incoming clock event. But then I have like latency problems. I need to react on it immediately, and depending on the code that's triggered by this timing event, I can just have like node messages coming out of it that just like phase around. But it's very easy to do, just like basically on every incoming clock message you trigger a clock event. What you can do as well is use a phase lock loop where you have your own timer running internally, and it adjusts its frequency and its phase to the incoming clock. And then even if you have jitter on the incoming clock, you can filter it out. Or what you can do as well is just like pull the synchronization around, so that if you have like a synthesizer has a bigger audio buffer and a synthesizer has a smaller audio buffer, you can filter it out by delaying or actually playing the clock in the future. I don't know if that's very clear, but you can basically phase out your own clock, which is pretty useful if you start to change devices. So, but that's when the really horrible stuff starts to happen with the phase lock loop. You need to have a pretty quick timer to be able to cover the whole range of MIDI tempos, which goes from like 20 BPM to 300 BPM, which is actually an order of magnitude bigger. And it turns out you run pretty quickly into numerical problems because you're using integer values, 32-bit integer values, for example, and the precision of the fixed point arithmetic doesn't hold up. So you start to have like, it's working perfectly with 120 BPM. If you use 121 BPM, it's going to start to shake around. So you have to kind of find fixes for that. A way to do that is to avoid doing a lot of calculations inside the timing code itself is using top half and bottom half IEQs. So you basically have a timing event setting just a flag. You need to recalculate my clock, for example, and that's going to be done sometime later on. It's not that really important when the filtering happens, but the actual timing code needs to be as fast as possible. So that's one way to design it, which I took from kernel development, that you have like hard, time-critical things happening and then parts of it that are not so time-critical. A big issue as Skipped actually is now if you start to have concurrency, you have your hardware running on the one side, and then you have your GUI code running on the one side, and then you have the whole sequencing and MIDI control part running on the other side. If you start to use threads, and basically if you use threads, you need an OS. So there's quite a lot of real-time OSs out there for embedded platforms. Some of them are open source, some of them are pretty expensive. But it turns out that you end up having quite a lot of complexity as well, and like, of course, overhead as well, especially data overhead, because every thread needs to have its own stack space. I decided against it and decided just basically to have this pretty simple driver main loop architecture using interrupts. So if you look into the source code of the framework, you're going to see this big run loop. Checking some flags from the top half, then doing basically what the firmware is doing, and then a lot of very specialized, optimized interrupts handling MIDI. Like incoming MIDI bytes are just stored in the ring buffer and then parsed later on, but MIDI clock bytes are acted upon immediately. Then you have I/O polling, which is taking place in an interrupt as well, and basically all the rest that's not that important is just running in the main loop. And the latency of that is not really tight. So I skipped this one part about the hardware, which is another part which needs some pretty tough real-time sometimes. It depends on the hardware. So for example, if you need to bit bang external chips, you need to take care of some timing constraints. You have to have a clean clock, you have to react in certain ages in a specific time. And another part of it is I'm using shift registers to poll the input. So basically I have like 16 buttons, I think, to poll. And you need to poll them fast enough so that you don't miss a click, for example. So that's this whole kind of bottom half, which just like reads in the shift register, and the top half, which is going to parse it and generate the events later on. You can also always use, if you can use the inbuilt hardware capabilities of the Atmel, go for it. Like for example, for SPI communication, that's a huge time saver. It's just like trigger SPI transfers in hardware and then have some interrupt when it's finished, to have some kind of DMA-like capabilities. If you're using the new X Mega device by Atmel, you have like a pretty nice DMA capability and like interrupts that you can chain, and interrupts acting on much more different flags than on this first Atmega. So if you can use it, they're starting to get available. Go for the X Mega. So that was the part about timing, which is, I think, the part I spent the most time on. It's still not working right exactly. I think I'm starting to read in this whole medical and nuclear hard real-time stuff, how they're going about it. And I think there's a lot that can be said in 1 year about it. And now I'm getting to the fun part of the talk, is like debugging techniques. If you do coding, you know that you spend quite a lot of time just fixing bugs. It's actually much worse when you're starting to do hardware near programming, embedded programming, because on the one side you have like this restriction of code space and RAM space. It can happen pretty quickly. For example, just a stack is overwritten, and you're just wondering what the hell is happening with the device. And then you also have the issue that you're actually running on real-world hardware that you can touch, that mostly, if you solder it yourself, you're not sure you solder it correctly. And you can have like all kind of weird issues creeping into that through the fact that you're running it on hardware, and then every time you're actually testing the device or building stuff on it, you're interacting with it as well. So you have these kind of weird Heisenberg's bugs happening. What happens very often as well is you have toolchain bugs, so that the compiler just generates crappy code, and you spend some time hunting it down. Especially like if it crashes, you don't see like segmentation fault, you just see stuff happening. And the best thing was I didn't initialize the external RAM, so it would like run for a few milliseconds with floating on the external RAM lines, and it would do all kinds of stuff. Like if I looked at it this way, it would start correctly, and if I looked at it this way, it would not start correctly. So I started to look for shorts and started to like stress test the device, see where it was coming from. Like maybe if I just press this button, it will work. And at the end, it was just one line of code that was faulty. I spent like, I think, 2 weeks hunting that down. I actually opened like 100 devices and swapped the capacitors on everyone. And at the end realized, okay, it was just one line of code. So you need to keep your eyes, your ears, everything open, and always question, is this coming from the software? Is this coming from the hardware? Is it my fault, or is it maybe the toolchain's fault? Often it's your fault, but it's often it bites you in the head, like you're searching for something, and like 3 days later you see, okay, it's not working with GCC 4.2, and I need to use GCC 4.2.1. And that's where this examining compiler output comes in pretty handy. When you see it just misses a register when an interrupt is happening, you have to be aware that can happen. So of the tools you can use to debug the whole thing, I think the most useful is actually the oscilloscope, even if you're working with code, because you can just like see what the code is actually doing. If you're trying to toggle a pin, nothing happens, and you see it just like a half voltage on the scope, you know that maybe a hardware problem is involved. Or if you see it happening irregular times, you can see that's all the stuff you can see with the scope, basically just like putting a probe in. You can look for voltages, for shorts, you can trace communication if you have like a memory scope. You can look on different channels at one time if you have a multi-channel scope, which is pretty useful, like trigger on one and look what the other one is doing. You have a lot of tools on the oscilloscopes as well, where you can like measure the width of a peak. So what I like to do to measure, for example, the CPU usage of an interrupt routine is just like trigger a LED at the beginning and pull it down at the end, and then you can just like use the PVM measuring on your scope, and it shows you like 30%, 40%. It's actually pretty nice. The one thing you need to think about is when you design your PCBs, just put a lot of test points everywhere and label them. So you don't have to go hunting for the serial interface and go like, oh, it's this pin, and then just destroy the pin by putting the probe onto it. One thing that's pretty useful as well is a logic analyzer, which is basically a digital multi-channel oscilloscope, and usually comes with software. It can debug protocols. So if you're debugging SPI communication, if you do it on a scope, you're gonna go nuts. And there you can just see that maybe the address is wrong or that the command is missing. So logic analyzer, you can buy them for €100, like small USB logic analyzer that are actually sufficient for microcontroller programming. Now I'm going to show some tricks I use when debugging stuff. So one thing that's pretty nice is to use a piezo and connect it to different test points. So if you have like a regular clock interrupt, you can hear it if it changes in pitch. You can hear the latency is changing. You can hear when specific events are happening. And the pretty nice thing about piezos and not using LEDs is you can hear frequencies much better than seeing brightness. And you don't need to look at the circuit to know if it's working, actually. You can just like, if it goes like, pick, 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 you know it's working correctly. And if I press this button, it goes like, you know, okay, something is wrong, without having to look at it, and you can concentrate on the code. So it's pretty nice, especially if you're synchronizing stuff. You can hear shifting clicks pretty easily as well, because they change in texture. But of course, the other big debugging trick is using LEDs and showing states in LEDs and just having them blink. And you can hook up the scope to the LED and have that as well. And it usually doesn't add any latency, because you're just using a set bit, clear bit instruction to set or clear the LED. But of course, that's just like useful for a few bugs, especially if you're working with parsers. But most of the time, it's very useful to actually log and print stuff. The bad thing about logging and printing is that actually modifies the way your software behaves, because you're using the inbuilt communication channels, and it's going to add latency, it's going to modify your buffers, it's going to modify your state. So I wouldn't advise using that for pretty low-level bugs, or especially timing bugs. Just don't use printfs to debug those. It can be pretty useful for like high-level stuff. On the other hand, that's the kind of bugs you should catch and unit tests or in code that runs on the host before you go over to the device. You can also log using, just not text that you can trace, but you can also use, in my case, I use MIDI. I send out MIDI notes for different states, so I hear like melodies depending on what happens. And if the melody goes wrong, I can put them on minor scales and chords and stuff, so I can, if it sounds bad, then probably something is wrong. So it's pretty nice as well. And depending on the device you use, the kind of channel you have, if you're building a DMX device, you can just like kind of show patterns and then see immediately if it's green, okay, then it's not good. So there's a lot of creative stuff you can do with logging and printing, actually. And of course, what you can use is using JTAG or PDI or debug wire. In the AVR case to actually read out the internal state of the device, write it also as well. You can set breakpoints, you can read out the memory, you can write the memory, and basically hook up a debugger to your device. So you basically use an external adapter and then use some bridge to GDB and then use GDB to interact with the hardware. So it's basically as if you were running a program in a debugger on the PC. The bad thing about it is that GDB is not very clever about using the JTAG resources of the Atmel. So it has just like 4 breakpoints, I think, and 1 memory breakpoint. And if you start your single step, it will pretty quickly overflow those breakpoints, and it will just like take 5 seconds to do a single instruction step. So you start pretty cheerfully debugging your code, and then just like step and next step, and then just like, okay, screw this, it's not working. So what I actually did is take the JTAG capability of this JTAG to GDB bridge and add JavaScript on top of it. So basically just use the JTAG primitives and add JavaScript to it. And the JavaScript debugger can now also parse elf debugging information to look up like which variables define at this line at which part in the memory. And that's actually much faster than using GDB for that kind of stuff. So you can basically put in a breakpoint on a specific function and tell the JavaScript to just log the register status to a file, and then later on going back to the file and seeing what happened. And it's just much more lightweight than GDB, and basically makes your device pretty usable. It's going to hang a bit, but it's not like the GDB stuff where you just stop doing it after 10 minutes. So this JavaScript debugger is actually a pretty involved thing as well. It's also in the Git repository. It's a bit usable, but if somebody is interested, I think the code is pretty clear. And it's actually pretty nice to just like do custom debug environments for it can parse C++ structures, so you can just like basically interact with C++ structures from the JavaScript. And now the funniest part is stress testing devices. It's actually hardware. A lot of bugs come from the hardware itself, and especially in the MIDI controller case, where you're using it in the techno club at 4 in the morning, with strobos going on and everybody's sweating. It's actually pretty useful to test the device for physical abuse first. And you have a lot of test environments that are pretty expensive. Like companies do that for CE testing and stuff like that. A lot of the testing you can actually do for locals at home. So for example, if you're testing for temperature, like if the electronics is going to work at certain temperatures, if the casing is going to take the physical stress, if it goes hot and then cold, stuff like that, you can just basically put your device in the oven and let it run at 80 degrees Celsius or 100 degrees Celsius and basically look what's going to go first. In my case, it was always the Chinese display that would just like stop working at first. So you can basically put it in the oven, then put it in the fridge, then put it in the freezer, then put it in the oven back again, stuff like that. It's pretty cheap, and it shows you if like you do it 5 times and this screw breaks, okay, maybe I need to up the tolerance on this one a bit. You can do vibration testing as well. The best I found is just put it on a subwoofer in a club. We can use like your washing machine or a car, like everything you have. The mill is pretty good as well. and just let it on there for 3 days and then see if something broke afterwards or stuff like that. Static discharge testing, you can do it pretty easily with a piezo lighter. You just take out the piezo and produce like 15 kilovolt spikes, and just take this one and zap the device at different points of entry from the casing. In this case as well, it was the Chinese display that would go at first all the time. And I actually had to fix the PCB of every single display because it's just weirdly done. But it's pretty nice to check out stuff, and it's pretty incredible the amount of abuse the AVR can take. Like you can zap 15 kilovolt spikes into the clock input, and it will continue to run, and all that kind of funny stuff. And of course, what you can do is just like kick abuse it, and then just like try to break it, and actually go as far as possible to break it to see what's the breaking point. And another thing you can do with stress testing is if you have protocol inputs like communication channels, it's just like using fuzzying from the security approach, just like sending a lot of random data or just like kind of crafting careful packets. Basically, as if you wanted to own it and you go with that kind of same mentality, and it makes just for pretty robust embedded firmware. I don't think a lot of people are doing this because when you start to take, for example, MIDI fuzzing, I started to just like check out different synthesizers, what they would do. And I think not a single one could take the abuse, like all just locked up in different kind of ways. And what you can do on a software kind of way to test out delays and interrupts, and it's just add delays to your interrupt routines, for example, so to simulate like kind of big load and see that it's going to stop working at this moment in this way if basically it just takes too much time to execute, and then you can know how much basically buffer you have before it starts missing interrupts, for example, or you start missing bytes. If you have like communication channels, just like try to fuzzy them at the full speed and see how much, if it's going to work, if it's just going to hang, if it's going to crash, and basically adjust the code that way. So that was basically all the stuff I discovered in this 1 year. And as I said, it didn't show any kind of technical detail, but I have a few blog posts on my website where I show like lots of assembler dumps, and this is why G++ is bad, or that kind of thing. You can check it out at reinvasion.com, and the whole code is available at GitHub. The JavaScript debugger I think is on there as well, I'm not sure. I've got the whole CAD, CNC software that generates the PCBs with test points and all that kind of stuff is there as well, and you can follow me on Twitter, ask me questions there. So are there any questions? I wonder if there's a way to stop that.
Okay, so you can come up here. I have a mic, or there's one back there.
Have you tried to use an AM radio set for debugging?
I was asked if I ever used an AM radio set for debugging, but I didn't. No.
Similar to the piezo.
Yeah, I think so. Like using audio stuff is pretty nice because you can always focus on a different thing. Any other questions about C++?
My question is not about C++, it's about your test environment. I was a bit confused at the beginning when you said you could build, I thought it was an emulator for all of the interfaces, and then do unit testing against the emulator. Is that what you were doing?
No, what I'm doing at the moment is using, the question was if I'm using an emulator for the unit testing. What I'm actually doing at the moment is using mock objects. So I have like this UART object, and I have a special version for it for macOS 10. It's going to use the real UART for maybe, or just like log the communication. So that's what I'm doing at the moment. But there's this new AVR simulator called SimAVR by BuzzEra, I think the guy's called, which looks pretty nice, which has like hardware simulation capabilities where you can actually, like simulate the levels on the UART, and then basically simulate the whole interrupt thing. Because when I'm doing the mock object, I don't have any interrupt coming in. It's basically just like calling OS functions. And that's what I'm aiming for, is just like having the real hardware simulated so that I can know that this takes 3 clock cycles and that kind of stuff. So that's work in progress.
Okay, cool.
Is there any other question? I think there's one over there.
Thought it was on.
Maybe you can just shout.
You talked about stress testing and temperature and vibration tests. Any specific tools for ESD tests?
Sorry?
Electronic discharge.
Yeah, I'm using this, the question is if I use any tools for static discharge. So this is all pretty amateurish, but it just like kind of gives me a feeling what it is. I use a piezo lighter that produces, like, to light the gas, it uses a 15 kilovolt spike. And you can actually add some kind of capacitor and resistor to make it more like the human testing model that is used for ESD testing. But basically I just zap it with my piezo light, and if it pretty much takes the zap at every input, I'm like, okay, this should be okay. I think I started doing that when I was playing with my controller in the club, and it just like stopped working every time the stroboscope came on. And it wasn't actually the device continued running, but it was this Chinese display that didn't take it. So it's just to give you a kind of a feeling what needs work without spending like 5,000 euros in testing. Any other questions? All right, so thank you very much.